Hola, hi, this is Al, your statistics instructor. Let's get to work. So, in this video, what I would like to do is finishing a homework problem, a problem that we didn't have enough time to work on together during our last lecture. Okay, so we have the following process. Y at t equals w at t plus beta times w at t minus 1, where wt is going to be white noise, Gaussian white noise, okay, with mean 0 and variance sigma squared. In another video, we have already obtained the spectral density of that process. Which, as you can see, it's a moving average of first order. So what we're going to be doing in this video will be obtaining the normalized spectral density of that process. Okay, so first let me rewrite the process that we are interested in here. So process, it's a moving average, first order, and it's defined as follows. Let's see, y at t equals w at t plus beta w at t minus 1. And as we said, wt is IID, normally distributed, with mean 0 and variance sigma squared, where wt RIID, normally distributed, in 0 variance sigma squared. Okay. Okay. So, as we said, what we want to do is obtaining the normalized spectral density. Okay. So, solution, we are looking for the normalized spectral density. That's what we want to obtain. So, first, let me remind you what the definition of spectral density is. Then we're going to contrast that with the definition of normalized spectral density, and then we're going to apply the definition of normalized spectral density. Okay, here we go. So first, definition of spectral density. So what we're going to have is f at w equals, and it's given by a summation, and that's gamma at k, the autocovariance function at lag k, times e to the power negative 2 pi. Let me find pi, negative 2 pi w I k, where I represents the square root of -1. Let me just finish here that definition, and then I'm going to remind you what I represents, where I represents the square root of -1. Okay. Okay, so that's the definition of spectral density. Okay. Let me remind you that we have this alternative formula for the spectral density and how we obtain that alternative formula. So to obtain that alternative formula, what we're going to be doing is breaking this down into 3 different terms. Okay, so first I take gamma at 0, gamma at lag 0. Okay, and then I'm going to have that sum that we have here. We're going to do that sum from -1, I'm sorry, from -infinity up to -1. Okay, then I'm going to have this sum starting at k equals 1 up to infinity. Now what we could do here is use the fact that the autocovariance function is symmetric. So let me rewrite this. So this is the same as gamma at -k. And now note something where, well, when k equals -1, okay, when k equals -1, then this, right, you would have -k times 2 pi I w. Well, then you would have positive k. If you had k equals -2, it would be the same as 2 pi wi times -k, and that would be, instead of a -2 for k, you would have positive. Okay, makes sense what I'm saying here? So if you have this negative here, and this should be a lowercase to be consistent, lowercase, lowercase, lowercase. Okay, so again, what I'm saying is that note that when k equals -1, right, k is going to be 1. When k equals -2, then you're going to have +2, and so on. And since gamma at -k is the same as gamma at k, we could have this instead. This is the same as k goes from 1 to infinity, gamma at k, because of the symmetry, right? And then this could be just positive k, and that is the same. Agreed? Yeah? Okay. So then what we could do is just factor out the autocovariance function, and it would be the autocovariance function times e to the power 2 pi wi k plus, and then we would have another exponential, but with a negative in front. Okay? Make sense? Okay. And then let me remind you that if you use Euler's formula, you could rewrite the sum of these two exponentials, right? So by Euler's, let me say this, using Euler's formula, then you have this e to the power 2 pi w I k, that is the same as cosine of 2 pi w k, we don't need the I here, plus I sine of that same angle. Okay, now here we want sine instead of cosine. Okay, now let's do the same with the negative version of the angle. So if we have e to the negative 2 times pi w I k, we're going to have negative 2 pi wk, and we're going to have negative 2 pi wk. And then let me remind you, recall that cosine of A equals, well, cosine of negative A equals cosine of A for any A. And that sine of negative A equals negative sine of A. So if we do that, now this, the second equation, looks like this. Cosine of negative 2 pi wk is the same as cosine of 2 pi wk, and this one here, we could pull out that negative sign. Okay, now if you do the sum of this one, let me call it Roman numeral 1, and then this one Roman numeral 2, if you do 1 plus 2, what you end up with is this, e to the power 2 pi w I k plus e to the power negative 2 pi w I k is going to be the same as cosine of 2 pi w k plus cosine of 2 pi w k. So we have 2 times that cosine, and then we have plus I sine of 2 pi w k minus I sine of 2 pi w k. These two terms cancel out. So that's what we have instead of the sum of those two exponentials. So let me just copy paste this one and place it here. It's going to be useful. Now let me copy paste this one. Oops, sorry. So I'm going to substitute this. Oops, not what I wanted to do. Let me just copy paste that again. And here, what I have is oh my god, let me rewrite it then. Summation of k goes from 1 to infinity, and then we're going to have 2 times gamma at k cosine of 2 pi w. Well, So 2 pi WK. Makes sense? So that would be F at W, the normalized density. Okay, so that's the alternative formula for the normalized density. Okay, so let's talk about the, I'm sorry, this is just the spectral density, the regular spectral density. Okay, so you could find it like this. This is the definition. This one here is an alternative formula. Okay, so now let's talk about the normalized spectral density. So there's a relationship between these two. Okay, so the notation that we use to make a distinction between the normalized spectral density and the regular spectral density is this. We use F star to refer to the normalized spectral density. So one way of finding it would be like this. You have the spectral density and you divide that by the variance of your process. So in this case we are using y's to refer to that process. So let me write it down like this. Variance of your process y. Now, another possibility would be, you know, that another way of referring to the variance of a process would be using the autocovariance function. So that is the same as gamma evaluated at 0. Okay? And you guys also know that if you divide the autocovariance function by gamma at 0, you end up with the autocorrelation function, right? So let me just copy paste this one, and this is going to be rho, the autocorrelation function, instead of the autocovariance function, right? Because all that we're doing is dividing this by gamma at 0, okay? So that's the main difference between the spectral density, this is the spectral density, and the normalized spectral density. So spectral density this one here, using the autocovariance function, this is the normalized spectral density, which is just take the spectral density and divide by the variance of the process, or in other words, the spectral density divided by gamma at 0. Okay? So now we are looking for the spectral density for an MA1 process, a moving average of first order. So something that we did in another video is finding the autocovariance function. Okay, so let me remind you what we ended up with there. Okay, what we showed there is this. Let me just say this. Autocovariance function. So it can be shown that, and we actually did it in another video, but I don't want this to be too long, so I'm going to be referring to the other one. So it can be shown that gamma at 0 for a moving average of first order happens to be sigma squared of W, okay, so the variance of the innovations of those W's, okay, plus, well, times 1 plus beta squared. We also showed that gamma at lag 1 or -1, because we know that it is symmetric. In that video we did it for 1, but then you got the other one for free. So gamma at 1, which is the same as gamma at -1, equals beta times sigma squared. Beta times sigma squared of W. Okay, so the variance of the W is not the process. And then something else that we showed is that gamma at K, for K greater or equal to 2, happens to be 0. For, you know, K's such that the absolute value of K is greater or equal to 2. So that's the autocovariance function. But we know that the one that we want is the normalized spectral density. So we need the autocorrelation function. So since the autocorrelation function is just the autocovariance function divided by the autocovariance function evaluated at 0, so the autocorrelation function, that's the one we want. So rho at 0, right? Let me just copy paste this. So rho at 0, of course, since it's gamma at 0 divided by gamma at 0, that is just going to be a beautiful 1. So it will be this divided by itself. That's just going to be 1. Okay, let me erase that. Now let's find the autocorrelation function at lag 1. So we want to find rho at 1. Rho at 1 equals gamma at 1 divided by gamma at 0. Oops. Let me do this. It's better. I just want to copy this one. Let me see if I can do that. There we are. So thing is, what we're doing here is dividing gamma at 1 by gamma at 0. So let me copy paste that from what we have up here. That's gamma at 0. Okay. So what we end up with here is just beta divided by 1 plus beta squared. Okay, so let me just copy paste this, and then the variance of the innovations well, those two sigma squares are cancelled out. Okay, so that's rho at 1, and since this is 0, then rho at lag k, when the absolute value of k is greater or equal to 2, is just going to be 0 as well. Okay? So finally, applying the definition, let me apply this one here, the alternative definition. Okay? So in this case, f star at w happens to be gamma at 0, I'm sorry, rho at 0, the autocorrelation function, which is 1. So let me write that one down. Plus 2 times, and then when k equals 1, that is just going to be rho at 1. Okay? So rho at 1 times cosine of 2 pi w times 1. So let me just copy paste this one. And k equals 1, so that's what we want. Okay? And then when rho, when rho it's evaluated at k equals 2, that's going to be 0. K equals 3, that's going to be 0, and so on. Makes sense? So these are the only terms that matter in this case. After lag 2, this is just 0. Okay? So finally, what we end up with here is 1 plus 2 times rho at 1. Let me copy what rho at 1 is this guy. Times cosine of 2 pi w. And that's it. That happens to be the normalized spectral density for a moving average of first order. So as you can see, the only difference between the spectral density, which we have here, and the normalized spectral density is this, that for the spectral density you use the autocovariance function to calculate it, and for the normalized spectral density you use the autocorrelation function. Okay? Other than that, they are very, very similar, and you can get the normalized spectral density by just dividing the spectral density by the variance of your process, or in other words, gamma evaluated at 0. Okay? And remember also, let me underline this, why are we interested in the spectral density? Well, the spectral density, when it's estimated with data, well, you end up with the periodogram. And the periodogram allows you to construct a graph, right? The periodogram is a graph that allows you to identify the important frequencies in case you have seasonality present in your time series. Okay? Okay, so that's it. Take care. Bye.